In this lecture, we will discuss about the quantum harmonic oscillator. But before we initiate the discussion about the quantum harmonic oscillator, we should have some knowledge about the classical harmonic oscillator. In general, oscillations are found throughout the nature. For example, in case of electromagnetic waves, vibrating molecules, and in the T branch. So, in different cases, we observe some types of oscillations. And we have learned in Newtonian mechanics that if some mass is attached on a spring and if you pull the spring, then there will be oscillation, and this is like some simple pendulum. So, let us begin the discussion of classical harmonic oscillation with an example of mass and spring system. So, a simple harmonic oscillator is a particle or system that undergoes harmonic motion about an equilibrium position. This line is very important. So, what do you mean by simple harmonic oscillator? So, the answer is a simple harmonic oscillator is a particle or system that undergoes harmonic motion about an equilibrium position, such as an object with mass vibrating on a spring that I told before. That is, some object that is attached to a spring and it is vibrating. And in this section, we will consider oscillations in one dimension. Suppose a mass moves back and forth along x direction. So, the mass is attached to a spring and it is moving back and forth. Basically, it is vibrating along the x direction and about the equilibrium position x is equal to 0. In classical mechanics, the particle moves in response to a linear restoring force given by Fx is equal to Kx. In some books, we write Fx is equal to minus Kx, as it attracts the mass towards the equilibrium. But if we consider the magnitude only, then the value of the restoring force F, that is equal to K into x. What is x? X is the displacement of the particle from its equilibrium position, and K is a constant. Sometimes we call it force constant. The motion takes place between two turning points, x is equal to a. We have observed that if the mass which is attached to the spring, if it vibrates, then it must vibrate between two turning points, that is where the amplitude is maximum, that is if we consider a positive amplitude, and if we consider a negative maximum amplitude. So, those positions we are calling that there is two turning points, x is equal to a, where a denotes the amplitude of the motion. The position of the object varies periodically in time with angular frequency omega is equal to root over of k by m, as the mass vibrates continuously. So, the position of the object that should vary periodically with respect to the time. So, there should be some angular frequency of the vibration. So, what is the value of the angular frequency? We know that omega is equal to root over of k by m, where k is the force constant and m is the mass of the object. So, omega, that is angular frequency, it depends on the mass m of the oscillator and on the force constant k of the net force. And the x, that is displacement can be written as a cos omega t plus phi. as the vibration is periodic in nature, so the displacement that should be represented by some periodic function. So x can be represented as a cos omega t plus phi. And we also know that the total energy E of an oscillator is the sum of its kinetic energy k, that is equal to m u square by 2, and the potential energy ux is equal to half k x square. We have all read about these facts, that is kinetic energy half m u square, where u is the velocity, and the potential energy is half k x square, where k is the restoring force and x is the displacement. We have not derived this, but I suggest you to read some textbook of vibrations or simple harmonic motion regarding the derivation. And total energy E is equal to half m u square plus half k x square. At the turning points x is equal to a, the speed of the oscillator is 0. We know about this from the expression of the velocity. You can find the expression of the velocity from here, and I think we have all read in your higher secondary classes about these facts, that at turning points x is equal to a, the speed of the oscillator is 0. Therefore, at these points the energy of oscillation is solely in the form of the potential energy E is equal to half k square. Why? Because speed u is 0, so there will be no kinetic energy term at the turning points. So at the turning points the total energy will be in the form of potential energy only, and its value will be E is equal to half k a square, because at those points x is equal to a. Now if we plot this equation, that is ux is equal to half k x square, so from the structure of this equation it is very easy to say that it must be a parabola. Why? You see the relation between u and x, that is u proportional to x square, u is equal to half k x square. So if we plot u as a function of x, then it must be a parabola. So how the parabola look like? It is the plot, that is in the x axis, that is the displacement, and this is what about ux, that is potential energy, and this is the parabola, and the expression is ux is equal to half k x square. So at a particular point x you can find the value of the potential energy. So these are the values of the potential energy described by the parabolic graph. So you can find the potential energy at any point x. So the value of the potential energy will lie on this parabola. Now on this same graph you can also represent the total energy E by a horizontal line. You can show the total energy E by a horizontal line. So the value of the potential energy will lie on the parabola, and you can plot the total energy by some horizontal lines in this same graph. You can also find the kinetic energy by the vertical distance between the, that is parabola. If this is the parabola and this is the total energy lines, so if you find the distance, suppose you have plotted a total energy line here and another total energy line is here, so the vertical distance between the total energy lines, so those will represent the value of the kinetic energy. Now the fact is that the kinetic energy k, that I have already told, that the kinetic energy k, that can be represented as the vertical distance between the line of the total energy and the potential energy parabola. So with this you can find the value of the kinetic energy. The potential energy well of a classical harmonic oscillator. So what do you mean by potential energy well of a classical harmonic oscillator? The motion is confined between turning points x is equal to a and x is equal to plus a, x is equal to minus a and x is equal to plus a. This that should be minus. the energy of oscillations is E is equal to half k square at those turning points. So you just look at this fact, that is, I have already told in the beginning of this lecture that whenever we consider some classical oscillator, from the observation we have observed that those oscillators vibrates between two turning points. So we can represent those turning points as x is equal to minus a, and another is x is equal to plus a. And at those particular points, the energy of the oscillation is fully potential energy, and the values are E is equal to half k square. These are the values. Now, the motion of classical oscillator is confined to the region where its kinetic energy is non-negative, which is what the energy relation says. Physically, it means that the classical oscillator can never be found beyond its turning points, and its energy depends only how far the turning points are from its equilibrium position. So we should concentrate on these particular lines, that as the classical oscillator is found between two turning points and it cannot go beyond these turning points, because at the turning points kinetic energy is 0 and total energy is fully potential energy, and that is the maximum energy. If the object goes beyond these points, so in that case kinetic energy will be negative, which is not permissible. So the classical oscillator can never be found beyond the turning points, and its energy depends on how far the turning points are from its equilibrium position. Because you see in the graph, suppose the objects can be found in this region, that is, this is plus a and this is minus a. So if you increase the distance, suppose plus a is here and minus a is here, that means its total energy will be higher. So total energy depends, that is, how far the turning points are from its equilibrium position. This is the equilibrium position. X is equal to 0 is the equilibrium position. The energy of a classical oscillator changes in a continuous way. It must change, because as it is vibrating, that means it is changing its position continuously and periodically. So the energy of the classical oscillator, that should change in a continuous way. The lowest energy that a classical oscillator may have is 0, which corresponds to a situation where an object is at rest at its equilibrium position. So when the object is at rest at equilibrium, that means in this position, suppose the object is at rest. So if the object is at rest in its equilibrium position, then what will happen? The energy of the oscillator should be 0 at the equilibrium. The zero energy state of a classical oscillator simply means no oscillation and no motion at all. So these lines are very important. The zero energy state of a classical oscillator simply means no oscillations and no motion at all. A classical particle sitting at the bottom of the potential well, we can consider this as a potential well. This is the potential well, this is the equilibrium position, and if the particle sits here with no motion, then we will consider that the particle has lowest energy, that is 0. A classical particle sitting at the bottom of the potential well, that is, when it sits at the bottom of the potential well, then the energy is 0. Now the point is that, suppose at the turning points, suppose the particle is here, that is, suppose either in this position or in this position. So from the equilibrium position, when the particle reaches to the turning point here, then after reaching the turning point, what happens? The particle change its direction and it comes back towards the equilibrium. And same case happens here also. Suppose from the equilibrium position the particle goes to this turning point, and after reaching that turning point it again change its direction towards the equilibrium position. So it means that at the turning points that reversing of the direction happens. So this case is very important, that at the turning point the particle or object reverses its direction of motion. Therefore, the probability of finding a classical oscillator between the turning points is highest and near the turning points that and lowest at the equilibrium position. I am again repeating the sentence. The probability of finding a classical oscillator is highest near the turning points and lowest at the equilibrium position. So we have to keep in mind that the probability of finding the classical oscillator is highest at the turning points. Why? Because you see, as it is reversing the direction after coming this particular turning point, so as it reversing the direction here, so it spends maximum time at the turning points, because it is reversing its direction here after reaching this point. So it have to spend maximum time here. So for this fact, the probability of finding the particle at the turning points is highest, and at the equilibrium position probability of finding the object is lowest. So we have to keep in mind this fact. But we have to also keep in mind that this is not a statement of preference of the object to go to lower energy. It is a statement about how quickly the object moves through various regions. It is a very important fact, that is sometimes this phenomena, that is, as we have said, that probability of finding the object near the turning points is maximum. However, the potential energy of the object is zero at the equilibrium, and we know that all objects tries to be in minimum potential energy. So from that concept, we may think in this way, that the probability of finding the object should be highest in the equilibrium, but that is not the fact. We are not saying in this way. Here the probability means, actually, that is, we are saying that is where the particle will spend the maximum time. So it is not a statement of the preference of the object to go to the lower energy. It is a statement about how quickly the object moves through various regions. As it is spending maximum time at the turning points, from that concept we are saying that the probability of finding the particle at the turning points should be maximum, and it is minimum in the equilibrium. So these are a general discussion regarding the classical harmonic oscillator. In the next lecture we will start our discussion regarding quantum mechanical harmonic oscillators, and we will observe that there are some difference regarding the classical harmonic oscillator and the quantum harmonic oscillator. So basically the difference lies, that is the minimum energy. The minimum energy for a classical oscillator is 0, that I have already discussed, and there is some differences regarding the turning points. Here I have told that the classical harmonic oscillators can be observed in between these turning points, that is plus A and minus A. It cannot go beyond plus A, or it cannot go beyond minus A, and the probability of finding the classical harmonic oscillator is highest at these turning points and lowest at the equilibrium. So these are the main facts. So these facts differ in case of quantum harmonic oscillators. So in the next lecture we will discuss about the quantum harmonic oscillators. and the content of this lecture uh, has been taken from University Physics Volume 3, and you can find a web page regarding this, that is openbc.ca. This is the name of the site. So from that website this content has been taken. So I request you to go through this content for further understanding, and I also thank you all who have listened this lecture.